For a lot of test takers, formal logic is one of the most intimidating topics. Not because it's difficult, but because they don't have any past exposure to it. The purpose of this video is to work through the concepts of formal logic from first principles and to establish baseline knowledge that you can build on. We'll start with definitions. A logical statement is a sentence or clause that is strictly either true or false. No maybes allowed. For example, I scored 177. That's either true or false. A truth value is the status of a statement as either true or false. Okay, so anytime you see a logical statement, you can think about substituting it out for its truth value if you know what that is. The negation is a logical operator that flips the truth value of a statement. Okay, so, for example, if I say I am happy, there's only two possible scenarios. Either it's true, I am happy, or false, I'm not happy. The negation is I am not happy. And if we work through the scenarios one at a time, in scenario one, where the initial statement is true, the negation is false. And in scenario two, where the original statement is false, the negation is true. And this is what we mean when we say it flips the truth value. True becomes false, false becomes true. In every scenario, it has an opposite value. That's how you know you have the correct negation. A tautology is a logical statement that always evaluates to true. A basic example of it would be A or not A. An event or its negation is always going to be a tautology. And finally, logically consistent. Two or more statements are consistent if it is possible for them to be true at the same time. For example, some kids like candy. And most kids like candy. Okay. Hypothetically, if 75% of kids like candy, both of these statements would evaluate to true. Since they can both be true at the same time, they're logically consistent. They do not contradict one another. Two statements would be logically inconsistent if they do contradict each other, if it would be impossible for them to both be true. So, for example, no kid likes candy. Would be incompatible with some kids like candy. Every once in a while, you'll notice a question stem in the LR section that uses the language logically consistent or logically inconsistent, so it's worth knowing this definition. Okay, there's four logical operators that commonly show up on the LSAT: not, and, or, and if. Logical operator, another name for it is logical function. A logical function, there's a typo here, but all good. A logical function accepts one or more logical statements as inputs and generates a single output. So like any function, it has inputs, one or more, and it's going to give you an output. In this case, one single output. So, like we were talking about a minute ago, logical statements have a truth value. So when you're working with these functions, you could write out the logical statement, or you could think of it in terms of the truth value. So let's say the logical statement is, I am happy. If I know that that evaluates to true, I can just write true. The negation of this would be false. Interestingly, you can do the same with if statements. So let's say you have the conditional A arrow B, which is if A then B, you can think of swapping out the logical statement A with its truth value. So hypothetically, if A is true, then this function tells you that the rule is being triggered, you have to move across the arrow, and you have to satisfy the necessary condition. If A evaluates to false, the function is not triggered, and you don't make any statements about B. Okay. And an or, we'll just do one of them. Let's say true or true. That would be equal to true. So or is a logical function. It takes two or more inputs, and it evaluates to true if at least one of the inputs is true. The only way or is false is if they're all false. Okay. Truth tables are the foundation of everything in logic. So all the relationships that we talk about, we can prove them using truth tables. This is not directly testable on the LSAT, but it is one of those topics where if you take the time to learn it, and it shouldn't be too hard to learn, but if you take the time to learn it, it might actually help you understand formal logic better. So we'll define two variables. A, the committee will meet at 6 p.m. B, it will rain at 6 p.m. And we'll explore the statement A and B. Okay, so what we do in a truth table is we have to first set the stage by mapping out every possible scenario. When you're dealing with two variables, there's four scenarios. A could be true or false, B could be true or false. I'll start listing the scenarios out. So we have scenario A and B. So in scenario 1, they're both true. In scenario 2, one is true, the other is false. In scenario 3, reverse it. Scenario 4, they're both false. So these are the four possible scenarios for the true false values for A and B. And then we can write out A and B, because A and B itself is a logical statement. So that means A and B has a truth value of its own. In scenario 1, where they're both true, where A and B are both true, A and B is also true. In scenario 2, where A is true and B is false, A and B is false. Likewise in 3, it's false, and likewise in 4, it's false. The only time when A and B is true is if all the inputs are true. Any LSAT book will tell you that the negation of A and B is not A or not B. Okay? And we can actually prove that using a truth table. So if we write down not A, okay, so this is where we look at the A column and we negate it here. So we write down the opposite. So it would be false, false, true, true. So the true changes to false and the false changes to true. Same thing with B. False, true, false, true. Okay. And then we look at not A or not B. So if this should have been negated. I did process it correctly as a negation. I think when I passed the stylus over it, it just didn't register. But this B should have been negated from the start. These values are all correct. So we have not A or not B. If either of these is true, then this is also true. Okay, so if you have false, false, right? False or false is false. false or true is true. True or false is true. True or true is true. And then you can compare this column, A and B, to this one, not A or not B, and notice that they're opposites. In each scenario, they have opposite truth values. That's how you confirm that they are negations of one another. Okay, moving on to ORs, different example. We'll use the context of the exam. Every LR question has 5 answer choices. Every question, for each question, there's exactly one correct answer. There has to be only one right answer. So we'll define 5 variables. Variable A is answer choice A is the correct response to the next question that you do on the LSAT, and following the same pattern for B, C, D, E. So when it comes to listing out the scenarios, it's not as complicated as it looks. There's only 5 scenarios. So we have A, B, C, D, E. 1, 2, 3, 4, 5. Either A is right, B is right, C is right, D is right, and E is right. And in each scenario, if you, like for example, scenario 1, if A is the right answer, the other 4 have to be the wrong answer. So variable B, the truth value would be false. B says B is the correct response. It's not, because A is correct. So we can just fill in the rest of the table based on that. And then we're looking at or, so let's say A or B or C or D or E. You have true or false or false or false or false. Since those are true here, the function evaluates a true. The same applies to each row. Okay, and interestingly, it's true in all 5 scenarios. Right, and this is the same as saying either A is the right answer, or B is the right answer, or C is the right answer, or D is the right answer, or E is the right answer. That's always going to be true. So this is a tautology. Okay. Same can be done for conditional statements. So if A then B, diagram it A arrow B. We have 4 scenarios. There's only 2 variables. Each one is either true or false. Scenario 1, 2, 3, 4. So we're just setting the stage. This is going to look like the AND example that we did. At least the setting, it's the same setup, same 4 scenarios. Okay. So with this column, we'll write A arrow B. And what we're exploring in this column is, when is this conditional satisfied and when is it violated? In scenario 1, this is the scenario where you're triggering the rule, because the sufficient condition evaluates the true. You have to go across the arrow. You have to satisfy the necessary condition. And this one is true. I think this might be the easiest one to understand in the table. Number 2, this is very important. This is called the rule breaker. Number 2 is the only way to violate a conditional rule. Okay, so the rule evaluates the false here. Like in scenario 2, this conditional is actually not valid. Because what's happening is you're passing the sufficient condition, you're going across the arrow, but then you're failing the necessary. Scenarios 3 and 4, this is where the conditional is trivially satisfied, because the rule is not being triggered. And if the rule is not being triggered, it can't be violated. It simply doesn't apply to these scenarios. Okay, so we could say Scenario 1, 3, and 4 are logically consistent with the conditional, and scenario 2 is logically inconsistent with the conditional statement. A lesser known fact is that when you negate a conditional statement, it turns into an and statement. It becomes A and not B. Okay. So I'll write out A again. Here, maybe I'll skip this column just so it's more clear. I'll write out A again as is. I'll write out not B. This is B here. This column is B. So when I do not B, I have to flip these. I have to flip the truth values. So true becomes false, false becomes true, true becomes false, false becomes true. And then I'll evaluate A and not B. I have true and false. That's false. I have true and true. That's true. False and false is false. False and true is false. And then I'll compare this column with this one. And notice how they're always opposite in every scenario. So scenario 1, this one is true, this one is false. False, true. True, false, true, false. And that's how you confirm that the negation of a conditional statement is an and statement. Okay. Then we can get into quantifiers. There's 4 main quantifiers that they use on the exam. So all, which refers to every single member of the group. Most is more than half, emphasis on more. If you have exactly 50%, that doesn't qualify as most. It has to be more than half. Some means at least one, and so there's a lower limit that's defined. There's no upper limit, which means that some includes most and all. None means literally 0. Okay. And let's talk about logical opposites versus extreme opposites as it relates to those 4 quantifiers. I'm not going to go through every scenario, but I'll give a couple of examples. So the LSAT, when we talk about negation, it's very important that we're looking for the logical opposite. We don't want to look for extreme opposites. So let's look at, to start, the logical opposites. Some and none. Okay, so let's define an exhaustive set of scenarios. Scenario. Okay, and let's use the example. Let's say some kids like candy. Some kids like candy. And no kids like candy. Okay. So scenario is that scenario 1 could be the percentage of kids that like candy is 0. I'll just say percentage of K is 0. 0%. In scenario 2, the percentage of kids that likes candy is more than 0 but less than 100. Which is the same as saying some kids like candy and some kids don't like candy. So 0 is less than the percentage, which is less than 100. And in scenario 3, the percentage of kids who like candy is 100%. Okay, I'll just say it again because this is admittedly very hard to read. So scenario 1, 0% of kids like candy. In scenario 2, some kids like candy and some kids don't like candy. So the percentage is between 0 and 100. It is not equal to 0. It is not equal to 100. And in scenario 3, 100% of kids like candy. Okay, so let's start off by looking at the sum. In scenario 1, where the percentage of kids who like candy is 0, sum is false. In scenario 2, where the percentage is between 0 and 100, sum is true. Right? Because for sum to be true, you need at least 1. And sum includes most and sum includes all. So even if it's 99%, sum is still true. In scenario 3, 100% of kids like candy, sum is true because sum includes all. Okay, and then let's look at none. In scenario number 1, the percentage of kids who like candy is 0%. None is true. In scenario 2, the percentage is between 0 and 100. None is false. Right? So for example, let's say 70% of kids like candy. Is it true that no kid likes candy? No, that statement is false. Scenario 3, 100% of kids like candy. Again, this is false. Okay. So notice how the values always flipped. False, true, true, false, true, false. Right? We have an exhaustive set of scenarios, and under each scenario, they have opposite true, false values. So that's what makes them logical opposites. Okay. Now, if we compare all kids like candy, all kids like candy, that's what I wrote in green here. This is the extreme opposite of this statement. No kid likes candy. So let's put all here and then go through these 3 scenarios again. So in scenario 1, 0% of kids like candy. Is it true that all kids like candy? No, that's false. Okay, let's skip scenario 2 for a second. Go to scenario 3. 100% of kids like candy. Is it true that all kids like candy? Yes, that's true. Okay, at this stage, it looks like these are opposites. The problem is scenario number 2, where the percentage of kids is between 0 and 100. It's not equal to 0 and it's not equal to 100. It's some number in between. It could be 10, 50, anything in between. In that scenario, both of these statements are false. They have the same true-false value, and that's why they're not logical opposites. Okay, I hope that helps. If you have questions, feel free to reach out and ask.